Hello Bobcats. So this video we're going to continue with the molecular geometry notes. So this will be molecular geometry part 2, and we're going to look at two different families. And so we'll start out here with PCl5, phosphorus pentachloride. Now at this point I will not be putting lone pairs on the outer atoms, just on the central atom. Now PCl5 is going to have a phosphorus with a chlorine here, a chlorine down, a chlorine this way here, and a chlorine here. And actually it would be best if we could picture this, where we have this chlorine going back and this one coming out like that. Okay, so there is our phosphorus pentachloride. Now if you look at it, electron domains, we have 1, 2, 3, 4, 5 electron domains, and we have 1, 2, 3, 4, 5 bonding domains, no lone pairs on the central atom. And so what that looks like is this, where we have, you'll notice we have chlorine up, these two chlorines linear here, and then these three are in a plane. So you can see the plane, right? So there's the three in the plane, and the way I drew it is that I've got one coming out of the plane, that's the one with the wedge, and one going back through the plane, which is the one with the dotted line. But you can kind of see that we have 180 degrees here, and then each of these are going to be 120 from each other, and then 90 here. So and I hope you can see that. I'm doing the best I can to show you this in space. Okay, now so what we have here is, it's called trigonal bipyramidal, because if you look at it, we have the triangle and then we have a kind of a pyramid. If you take and draw the lines up here, here, and then one from the back up to the chlorine, that's a pyramid, trigonal pyramid. But there's one on top and one on bottom. So there's a trigonal pyramid on top and a trigonal pyramid on the bottom. So we have what's called trigonal bipyramidal. And since these two are the same, the electron domains and the bonding domains are the same, it's same shape, trigonal bipyramidal. So the electron geometry and shape of the molecule are the same. And since there's 1, 2, 3, 4, 5, this is going to be sp3d. Think of that. 1 plus 3 is 4 plus 1 is 5. And this has different angles. It has 90-degree angle, it has 120-degree angle, and 180-degree angles. And I showed you that, where we have the 90-degree angle from here to here, the 180 from here to here, and then 120 from here to here. Or you can say from here to here is the 120. Now, what happens when we add a lone pair to it? So if we look at sulfur tetrafluoride, we're going to have sulfur with a fluorine on top and a fluorine on bottom, a fluorine going back and a fluorine coming forward, and then we have the lone pair over here. So here's what we have. We've got 1, 2, 3, 4, 5. We still have 5 electron domains, but now we only have 1, 2, 3, 4 electron domains and one lone pair. Now, since the electron geometry is based on electron domains, it's still trigonal bipyramidal. But now this shape is different. Every time we add a lone pair, the shape changes. And so the way you can look at this is, here's what we have for this one. So if you'll notice, if I place it the same way that I have it written, we have a fluorine up, a fluorine down, this lone pair that direction, and then we have this chlorine going back and this chlorine coming forward. So when I take the lone pair off, what we have here, if you'll notice, we go back and forth. In other words, if I look at it, it's going dun, dun. So this is a seesaw. You can see it. Here we go. Looks like a seesaw. Down, down, going back and forth. So we call that a seesaw. Shape. It's still sp3 dehybridized with 5 electron domains, and we're not going to worry about the angles. Then let's look at bromine trifluoride. Okay, so that's going to be a bromine with a fluorine up and a fluorine down, fluorine out, and then we're going to have a lone pair here and then a lone pair here. So now we still have 5 electron domains. 1, 2, 3, 4, 5. So it's 5 electron domains, but now we only have 1, 2, 3 bonding domains and 2 lone pair. And so remember, electron geometry is based on electron domains. There's 5 of them, so that's still trigonal, bipyramidal. But now we got to figure out the shape here. So what does that one look like? Well, here we have where we have the fluorine down, fluorine up, and fluorine out. And then we have a lone pair going back and a lone pair coming out. Can you see it? So in other words, the lone pairs are on the triangle part. You can see it. Let me put it down. Okay. Now if I take those lone pairs off, what shape do I have? It's called a T shape. See, it's linear. I mean, not linear. It's on a plane, so it's a T shape. Okay. So yes, it's very simple. It's T shape. And it's still sp3 dehybridized. We're not going to worry about the angles. We have one more. Let's look at I3 minus. And the way that is we have an iodine with an iodine here and an iodine here. And then we're going to have a lone pair, and then a lone pair. Okay, and so the lone pairs have been put on the trigonal plane, and so remember we still have 1, 2, 3, 4, 5 electron domains, but now we only have 1, 2 bonding domains and 3 lone pair. And the way that looks is here we have, if you'll notice, we have the iodine here, iodine, and then we put the lone pairs on the trigonal planar part. And so when we take those lone pairs off, what do we have? We have a linear molecule. Let me put that right up there. So that's going to be trigonal, bipyramidal, as far as electron geometry, because we're looking at the 5 electron domains, but this is linear molecular shape because we only have 2 bonding domains. It's still sp3 dehybridized, and that is it for that group. So you can call it the trigonal bipyramidal group, or you can call it the sp3 dehybridized group. And I like the term sp3 dehybridized. So that is that group, the sp3 dehybridized or the trigonal bipyramidal. Okay, one more group and then we're done. So the first one we're going to look at is going to be sulfur hexafluoride. Sulfur hexafluoride. Oops, I'm running out of SF6, sulfur hexafluoride. And what we'll have here is a sulfur with a fluorine, and then we got a fluorine here, a fluorine coming out, fluorine going back, and a fluorine going here. So, and I'm not going to draw the wedges or anything. You can kind of see that you have a square planar part here, and then you have these two linear to each other. So we have 1, 2, 3, 4, 5, 6, 6 electron domains, 6 bonding domains, 0 lone pairs. The shape is octahedral. And how do we get that? Here's what we have. So we have, if you look at it, we've got linear part, and then we got the 4 on the plane, right? So it kind of spins. You can kind of see it. So what it is we got 1, 2, 3, 4 faces on top, and then 1, 2, 3, 4 faces on bottom. So again, if I place, that'd be 1, 2, 3, 4 faces on top and bottom. So that's 8 total sides or faces, so octahedral. It's got an octahedral shape. And now because we have 6 electron domains, it's going to be sp3d2 hybridized. So 1, 2, 3, 4, 5, 6. And you've got 90 degrees and 180 degrees. So if you look at it, we have the 180 from here to here, and then from here to here is 90. And even from here to here is 90. So that is that one. Now if we take one of those away and we put a lone pair on there, so that would be, let's do bromine pentafluoride. So we'll have bromine here. We'll have a fluorine here. We'll have a fluorine this way, a fluorine coming out, a fluorine here, and a fluorine here, and then the lone pair down below. So we have 1, 2, 3, 4, 5, 6. Let me slow that down. 1, 2, 3, 4, 5, 6 electron domains. 1, 2, 3, 4, 5 bonding domains and 1 lone pair. Remember, it's still octahedral, so this is going to be the octahedral group. Now, in this case, what's that shape like? So here we have the lone pair. So remember, it's still octahedral as far as when we're looking at the lone pair, but when we take the lone pair off, what we have is this, because it's in a plane here, and if I drew lines up, there's a base of 4, and it looks like a pyramid. If I drew a line from here to here, if you look at it from here to here, here to there, and so forth, you get a pyramid. And so this is going to be, and because it's a square base, it's going to be square pyramidal. Again, it's still sp3d2 hybridized, but we're not going to worry about any of the angles. And the last one is going to be, let's look at xenon tetrafluoride. Now I know xenon is a noble gas, but we've actually been able to make it bond. It doesn't do it in nature, but we have forced it to bond. So let's do a xenon, and we're going to have a lone pair on top, a lone pair on bottom, then we're going to have fluorine here, fluorine here, fluorine here, fluorine here. We still have 1, 2, 3, 4, 5, 6 electron domains, and we're going to have 1, 2, 3, 4 bonding domains, and 2 lone pairs. Now, still octahedral group, so it's octahedral electron geometry, but the shape is this now. So if I look at this, I have, you can see when we have the electrons in that it's still octahedral, right? You can see the octahedral shape. But when I take the electrons off the lone pairs, what we have is a square, and then it's in a plane. So it's called square planar. So the shape of the molecule is square planar. And it's sp3d2. And it's all 90 degrees. Each one of these is 90 degrees apart. This one up here, I should have put 180 degrees because it's linear. So we know that it's going to be 180. That's what linear is. Okay. So there we have the other two groups. So the last one you can call the octahedral group or the sp3d2. And so since I'm going to stay with my theme here, we're going to call it sp3d2. But remember, all we have to look at is what doesn't change. So this one up here is the trigonal pyramidal group, and it's sp3d hybridized because it has 5 electron domains. And this is the octahedral group, or sp3d2 hybridized, and that's because it has 6 electron domains. And that's it for electron geometry, and I will see you next time.